Muñoz. So first of all, thank you so much for coming. I'm going to be very short because of said time constraints. We are delighted that we have two fantastic speakers in advance of the Vera Rubin Reveal live stream. We have Hiranya Peiris, who I'm sure you all know, who's going to be talking about the science behind the large survey of space and time. And we are also, by a nice coincidence, joined by Freddy Muñoz from Chile, who's the lead engineer for the Rubin telescope, who happens to be visiting us in Cambridge, and will be telling us a bit about the engineering of the telescope before we hear about the science.
Okay. Can you hear me properly? Hello. Thank you so much for the Institute of Astronomy for the invitation. It's a super nice coincidence to be here, and as time flies, and we are all very excited for the images that we are coming from the US. We will start this introduction. I'm the mechanical engineer for the construction of the Rubin telescope in Chile, so I'm happy to share how the process of such a unique telescope was over the last years. As every dream and every project starts with a napkin, and I'm sure Cambridge is familiar with this design. This is a 3-mirror telescope that we know has the ability to reduce all and minimize all the aberrations that will affect optical science. Plus, providing a wide field of view, at the same time provides a very compact and easy to stabilize structure. So this design has come through over decades and many years of development of ancient areas, I mean old areas, from Mersenne, Paul Baker, and familiar to Cambridge, Dr. Roderick Willstrop. In the US, Roger Angel and Tony Tyson took this design in order to adapt them for what they call the dark energy telescope in the late 90s of the last century. The goal of them was to have the abilities of the 3-mirror design in order to capture wide field for very tight science requirements. The napkin that we were talking about has this modified Paul Baker structure in order to provide for what will come later, the LSST and now Rubin Observatory, the required size for holding the telescope structure. I will move forward over this description, but at the very end, what I would like to introduce is how we convert this into reality. So these were the first draft of the optical design of this telescope, and this was the very first model of 21 of the dark energy telescope. How we move from this design to this, what we have today, is what we are want to share with you, okay? So for very tight science, for very unique science requirement, we need to push every engineer discipline to the limits. So we have here multiple systems with the most extreme demands that we have been facing in our institution down in Chile. We move very heavy pieces of the telescope. We need a lot of power to supply servers, to supply the telescope itself motion. We have large cranes, very precise hydraulics, industrial safety, and many other areas of engineering involved behind the science that is ongoing in the telescope. The main component of the observatories are the mirrors. So I will describe how the 3-mirrors optical design transferred to reality. This is the Rubin Observatory Simonyi Telescope 3-mirror sequence. The key here is that we create the primary and tertiary optical surface in a single monolithic glass. That's in order to keep the stability of the system and provide one single cell to support those to surface. And we control separately the M2 up there. So we have a 8.4 meters diameter main glass with an internal 5 meters diameter M3, and the M2 is 3.6. As equivalence, this provides a 6.7 meter diameter in the clear aperture for the M1 annular size. So this is a modified Paul Baker that needs certain structures to work as is intended. I will use this reference of Cambridge to provide a scale of how big is the mirror. This is the 36 inches telescope here in the Institute, and according to the research that I conduct, the dome is 27 feet in diameter. So our glass is 8.4 meters in diameter, so it will capture the entire telescope within its structure. We can see here not only the external 8 meters, but also the internal 5 meters as well. So this is the blank cast. It's borosilicate material casted in the Arizona Stewart Mirror Lab in the United States. 16 years ago, and went under 3 years of polishing processes. It's a 17 tons piece of glass with multiple honeycomb shape in order to provide lightweight and being able to control this mass at the remarkably higher speeds that the telescope moves. We participate, or our critical role on this process are the transportations. This is a scene from the US, how we move the glass from the mirror lab down to the Tucson airport and then to the Los Angeles port in order to ship the mirror to Chile by boat, by ships. We participate directly in the transportation. This takes a month over the sea and use very delicate transportation to move the container, the white crate that we see here, into our building. This is a very delicate process that requires precise control of every inch of the road from the United States down to Chile, because how delicate this material is. This picture that we have here is the glass with a protective film of OptiCoat. This is not the actual reflective surface yet. How we move this piece, we use a vacuum lifter. We do not have any metallic or mechanical fixture attached to the round of the borosilicate, but we pick up the glass just one time, for one in the life, from the optical surface down on its cells. So this is a picture about how delicate and complex is this lifting fixture in order to provide the ability to move from the container into the cell. The system has very tight requirements on thermal stability and settle time, because if we do not settle the mirror properly, it will create distorted images at the end. We call all this system the IoAs, the Active Optics Systems. We have 156 pneumatic actuators for the primary and 78 mechanical actuators for the M2. How they work, they are cardboard-sized cylinders that were controlled by software depending on how the waveform sensor images retrofits a laser tracker located in the optical axis. This is a diagram on how this system works. The laser tracker, a key feature here, it's located in this position in the optical axis and reads the entire surface of the M1, of the M3, of the M2, and from the camera, providing a mathematical model to adapt all these actuators to follow a specific shape according to the elevation of the telescope. Those systems are running today. After the mirror is transported or installed into the optical cell, we need to complete the process to remove the blue layer of OptiCoat and actually create the mirror and the reflective surface. This process was achieved successfully last year, something that took probably 30 minutes to complete, but 18 years in the making, including the glass and the coating chamber. So this is the final result. I mean, a high-quality, high-reflectivity mirror that uses one layer of aluminum, one layer of silver, and a transparent layer of silica to protect the mirrors from scratch. To achieve this, we only need 64 grams of silver for a cost of something of 100 pounds, and enough to create a 120 nanometers layer. It's enough to see the stars, so it's a good offer. Yeah. We repeat the same process for the M2, which is 3.6 meters. It's smaller, but we use the same facility, the same coating chamber, the same lower vessel, but the material is different. It was cast for a different company, Corning, in the East Coast of the United States as well. And you can see it's way more lighter than the primary, just 1.3 tons, but also as delicate as required, and with mechanical actuators as well at the end. So those are the description of the mirrors. The facilities has to do with the building that we are working with. Everything starts with an explosion. So same we did it in our mountain. We are located at 30 degrees south latitude and 70 degrees western longitude in northern Chile. This latitude coincides with those of South Africa telescopes and Australia telescopes. So we are in the same line for range. This is a map that shows our location in Chile, and the other largest telescope that you are familiar with, probably Rubin Observatory, are located here, and the BLT here. And the extremely large telescope project from ISO is also located here. For these decades, of 4 large telescope projects, 3 are located in this area. Our building is a 30 by 38 meters enclosure, 100 meters service area for the business, and provides all the utilities that the telescope requires. coating plants, clean rooms, network, a lot of servers, vacuum, oil, and the people that is required for assembly this. This is a time-lapse over 6-7 years of construction of the facilities in severe winter conditions with 200 workers and with specific heavy requirements. I'm actually quite proud of this cover that we get, because this is a good example about how science could meet industry. I mean, this is a 50-ton lift to microns. We use a 500-ton cranes to assemble the telescope. And this is the kind of activity that we conduct on the mountain. I mean, we assemble the telescope in pieces. It's not possible to assemble everything in the ground and just store it in the oil. So we do it by hand. I mean, the telescope at the end is roughly azimuth and elevation structures are the same in the range of 150 tons. Everything is supported in a just 70 microns oil film provided by the hydraulic plant of the observatory. This provides zero friction, so you are able to rotate this telescope by hand, and we have proof of that. The drives are actually quite powerful for the pointing and settle time requirements, but this corresponds to the enclosure of the telescope and the process of commissioning of the drives, which was part of my direct responsibilities during this project. As you can see, the final result, after all the surrogates are removed, is the motion of the telescope with the real glass. The image that we are seeing is before the first night, and we can see around how the elevation drafted. The video is getting lag a bit. Trust me that this is way more smooth. And the calibration screen is at the bottom. This is required to provide all the science for flat fields and to the combination that we have with our auxiliary telescope. This is another side view, which I just select to present to you, just to prove that this is possible to move this telescope by hand. This is Dr. Robert Lupton, which is a former alumni of the Institute. So he can, and he will be here in 10 days, so he can confirm all this information. At the end, our work ends with the telescope in motion, but we also are host of one of the most expensive instruments in the world, the largest digital camera in existence, provided by the Stanford Linear Accelerator from California. The instrument is the size of a small car, weighs 3.8 tons, and has all the elements for the optical corrections, including now 189 detectors for science, including 12 for guiding and wavefront sensing. This is the most critical and important part of the entire observatory. This is just a picture about how we transport all these elements into the telescope. This is directly our responsibility, have everything connected to the proper motion. And a fast description about how our filter works. We have the 6 bands. This comes from the Sirius driver of the telescope. We have the U, G, R, I, Zeta, and Y bands currently working and observing during the nights. This is a picture of the first night observing of the telescope in October last year with the commissioning instrument before the science camera, just to prove ourselves that the telescope is working and safe for the real instrument. Okay. I'm happy to address any questions at the end of the stream. Thank you for the speech.
Thank you so much, Freddy. So perfectly to time. Thank you. As we are running so tight, we're going to do any questions for both Freddy and Hiranya after the stream, about 4:20, 4:30. So just hold all questions until the very end. So now Hiranya is going to tell us a bit more, about the science behind LSST.
Thank you very much. Thanks so much for that great talk, Freddy. It's really great to have you here and benefit from your personal experience of working with this amazing facility. I'm just here to kind of pass the time, really, till we see the live stream. So I will try to entertain you a little bit about what we can expect. So as you can see, this project was conceived of in the mid-90s, and the paper called the Dark Matter Telescope which is from 2001 by Tony Tyson and Roger Angel and others. I remember seeing that when I was a PhD student. And so then this has been funded through the US decadal system, but it now involves 23 countries, and that's a lot of people. And I just wanted to acknowledge, before I get started with anything, what kind of amazing things that we can do when human beings come together and build something rather than destroy it. So in that context, I want to talk about bringing the night sky to life. So the mission of Rubin Observatory is capturing the cosmos. And it is going to do that with the Vera C Rubin Observatory's legacy survey of space and time. And I wanted to acknowledge also the fact that this is the first telescope that is actually named after a woman astronomer. It's the biggest national facility to get that honor. And so I wanted to acknowledge Vera's legacy. So what Rubin will do is to repeatedly scan the sky, roughly every 3 days, and do that for 10 years. And it'll cover half the sky in that mode. And many of you in this room have worked with the Sloan Digital Sky Survey. So that took data for about 20 years. It will do Sloan every 3 days over half the sky. That is the level of advance that we're talking about here. And by doing that, with the largest digital camera in the world, we'll create a ultra-wide and very deep time-lapse record of the universe. And what is that? That is a movie. It will be the greatest cosmic movie ever made. So in this mission to capture the cosmos, as we just heard, we'll have an amazing camera with a huge field of view. So the first element of making this movie is this wide, and it will also be fast. You heard about the Cambridge connection behind this unique 3-mirror design. So that will allow you to slew this enormous behemoth telescope really fast to do the southern sky every 3 days. And because we are going to build up this very, very deep image of the sky, it will be very deep, and it will reveal the low surface brightness universe. So wide, fast, deep is the main survey that LSST is going to do. And that will be the greatest astronomical movie of all time. So just to summarize this, it will repeatedly scan the southern sky every 3 nights for 10 years. And it will make a wide field survey in 6 colors that will span from the near UV to the near infrared. So when you see the images later, as you know, we can see the optical colors. Ruby can see a little bit further into the UV and in the infrared. So those images will have the colors adjusted to actually correspond to what we see. So there will be some level of false color, but it is actually quite true to what you would see. So on top of this, Rubin will have this time domain aspect. It's going to make a detailed time-lapse view of the cosmos. And it will be the first time that we've been actually able to survey the universe in that mode, space and time at the same time. So with these amazing capabilities, we are going to be able to do science that is actually very different, looking very close to us in the solar system, all the way to surveying 1,000 times greater space-time volume that has been possible before. And so these pillars include the Milky Way, a detailed map of the Milky Way, a huge survey that allows us to study dark matter and dark energy in unprecedented ways. We'll make a census of the solar system, and we will look at the changing sky and being able to map rare events and extreme events in the universe. I'll very briefly go through these different science pillars right now. So the changing sky. Rubin will see 10 million things changing on the sky every night. And so that allows you to uncover rare events And if you're able to quickly plot out the most important events out of this huge time stream and enable global follow-up, you could be the first to discover unprecedented events in the universe that we've never been able to see before because we have not surveyed the sky in this mode before. So at every point in the southern sky, over its survey period, it will take 800 images. And so it's able to then sample time domain events all the way from 3 days to this 10-year baseline. So we will be able to actually sample the time domain in unprecedented ways. So I also mentioned dark matter and dark energy. This is my wheelhouse. I'm very excited about the fact that we are going to have many different new ways to look at these questions of dark matter and dark energy, and homogeneously do that within one survey that is well calibrated and where we can work to understand all of the systematics. So in addition to being able to survey 1 billion galaxies, we will measure the impact of gravitational lensing on those galaxies. So we'll be able to do cosmic shear, galaxy-galaxy lensing, galaxy clustering, and we will be also able to leverage the changing sky aspect, the time domain, and do a supernova survey within the same survey and combine that information as well. The volume surveyed is so vast that we will see large numbers of very massive objects like clusters. We can bring that into cosmology, and we will also see rare events, such as gravitational wave lenses that actually capture supernova going off in them. So all of these put together is an incredible cosmological machine that is able to unpick dark matter and dark energy. And we will also be able to study the Milky Way in its context as a galaxy. It's a typical spiral galaxy. We will be able to unpick its accretion history, look at stellar populations within the Milky Way in great detail, and make a huge map of the Milky Way. There are many people here working on this science, and I really look forward to seeing what they uncover with this idea of the Milky Way as a model for galaxy formation. And then we will also make a census of the solar system. And again, this is the solar system in the context of other planetary systems. It is the one that we can study in the greatest detail, and being able to make a census of asteroids within that system will not only enable us to understand other planetary systems better, but also to protect ourselves from near-Earth asteroids that may collide with the Earth in the future. And finally, and I think this is the thing I'm personally most excited about, every time we've looked at the universe in new ways, we've found things that we had not imagined before. And because of this vast discovery space that Rubin is going to enable, we will find new classes of objects. We will definitely find new classes of transients. And we might discover physical phenomena that we have not seen before. So this is the discovery machine aspect that excites me the most. We already heard quite a lot about the amazing camera that we are going to have, 3.2 gigapixels, 6 filters, and it is mounted on this amazing telescope, the Muñoz survey telescope that is actually going to survey the sky very fast. And the part that didn't come across before, and I want to emphasize, is this amount of data that we're going to be actually getting that is actually unprecedented in terms of an optical survey. And I want to emphasize that the UK is doing its part to deal with this data. We process about 1/3 of the data and serve it out to the entire world. Our funding agency, STFC, actually invested £23 million into this project, and it is the, I think, the 3rd largest contributor to the project after the US and France. So we heard a lot about the camera. A single picture is going to take up 400 Ultra HD TVs to display in its full resolution. That's the scale of it. Each picture will be about 45 times the size of the full moon. And it is really amazing. So yes, we heard about the color filters. And so what do we get out of this 10-year survey with this amazing camera? It'll take images every 40 seconds or so. It's 20 terabytes of data a night. It's 500 petabytes of processed data. So it is big data in terms of its volume, its rate of arrival, and its complexity. And we are going to need amazing new algorithms to actually make sense of all of this data and turn it into science. And this data comes at us really fast. So 10 million alerts a night. It's not really an alert stream, it's an alert tsunami. And so these alerts come within minutes of being actually detected and cross-referenced. It's pushed out to the world essentially live. It'll make catalogs every 24 hours, and it'll make processed images every 80 hours. So it is the data rate that is just unprecedented. One aspect of this that, again, it's really worth highlighting is that it is data for all of us, for all of humanity. It's going to actually make data public and accessible to more people than ever before from an astronomical survey. And again, the UK is the host of the Zooniverse project, which is going to use this data and actually turn it into citizen science and engage people in terms of not just engagement in astronomy, but engagement in science. I'm going to end with this quote from Vera Rubin, because I think it's really perfect, and again, emphasizing this discovery space aspect of Rubin Observatory. Don't shoot for the stars. We already know what's there. Shoot for the space in between, because that's where the real mystery lies. And with that, I'm going to give the floor over to the stream. Thank you.